In this video, we're going to talk about concavity, what it is, and how it's related to the second derivative. So we've seen that the first derivative of a function, f of x, tells us when the function is increasing or decreasing. When the first derivative, f prime of x, is greater than 0, the function f of x is increasing, and when f prime of x is less than 0, the function f of x is decreasing. And we saw that we can use this to find relative maxes and mins. If the function is increasing and then decreasing, then we know that we've got a relative maximum at that point. So this is f prime of x greater than 0, and then f prime of x less than 0. And if the function is decreasing and then increasing, then f prime of x is less than 0, followed by f prime of x greater than 0, the tangent line to the curve is positive, the tangent line to the curve is negative, then that is a relative minimum at that point. Okay, so that's first derivative and what it tells us about a function. Now, what does the second derivative tell us about? It tells us about the concavity of the original function. So one definition of concavity is the following. A function is concave up over an interval if the first derivative, f prime of x, is increasing. So if the derivative is increasing, then it's concave up. And if the first derivative is increasing, that means that the derivative of the derivative, the second derivative, would be greater than 0 because the first derivative is increasing, therefore its derivative, the second derivative, will be positive. A function is concave down over an interval if the first derivative, f prime of x, is decreasing on that interval. And if f prime of x is decreasing, that means the derivative of f prime of x is negative. So that would happen exactly when the second derivative is less than 0. So let's take a look at this graph below, and let's think about a couple of points. Actually, let's think about a couple intervals. So we'll think about the interval from a to b. You know, what's the function doing there? Is the function increasing or decreasing? Is it concave up or concave down? What's happening over the interval from c to d? Is it increasing or decreasing, concave up or concave down? Same thing over the interval from e to g and from h to k. So think about each of those intervals, and over those intervals, is that function increasing or decreasing? Is the function concave up or concave down? So I'm going to pause and let you think about that for a moment. Okay, so from over the interval from a to b, so here's the function from a to b, we see that the function is increasing because if we pick any 2 points, we see that the function is increasing as we move to the right in x. We're going up in y. So over this interval from a to b, the function is increasing. Now, is it concave up or concave down? So we're thinking about the derivative of the derivative. So let's draw the tangent line to the curve. So there's the tangent line to the curve at that point, and then we can also draw the tangent line to the curve at, say, this point right here. And so what is happening to that derivative? Well, in both cases, the derivative is positive. F prime of x is greater than 0. Again, the function is increasing, so that will be true. The slope of the tangent line to the curve is positive. But what about the second derivative? So is the first derivative increasing or decreasing? Well, it looks here like f prime of x is decreasing over the interval from a to b. Why do I say that? Because if we pick 2 points and look at the first derivative, we see here we've got a positive slope. Here we've got a positive slope. Here we've also got a positive slope, but the slope is smaller. Like maybe this is a slope of maybe like 1, and this is a slope of, say, 1/2. And the slope is the derivative at that point, f prime of x, f prime of x. So as we're increasing in x, the derivative is decreasing, f prime of x is decreasing, and because f prime of x is decreasing over that interval, that means that we're concave down because f prime of x is decreasing, and that means that the second derivative, f double prime of x, is less than 0. So we're concave down and increasing over that interval from a to b. Now, what about the interval from C to D? So the interval from C to D, we could use purple. And what is happening to that function at that point? Well, as we go over in x, we're going down in y. So over this interval from C to D, we see that that the function f of x is decreasing. So the function is decreasing, and it's decreasing, so f prime of x, the first derivative, is less than 0 over that interval. And yeah, if we take any point and look at the slope of the tangent line, it's going to be a negative slope. It's going to be a negative slope, so it's going to have a negative derivative. And if we pick another point along that interval, so if we pick another point on that interval, say here, and we look at the tangent line there, we see that, yeah, we still have a negative tangent line, but it's even more negative. So maybe this is a slope of -1, and that purple one was a slope of -2/3. I don't know, just sort of estimating. But the slope has become more negative. It has become a larger negative number. And so f prime of x is also decreasing. It is becoming more negative. It is becoming more negative. And that means that f double prime of x is less than 0. So we're also concave down. So we are concave down over that interval. So from A to B, we were increasing and concave down. From C to D, we were decreasing and also concave down. What about the interval from E to G? For the interval from E to G, from here to here, what is happening? So we are decreasing. When we go over in x, we're going down in y. So for this interval, we are decreasing, and the first derivative, f prime of x, is less than 0 over that interval. What about concave up or concave down? So if we pick 2 points in that interval, like here and here, what's happening to the first derivative? So the first derivative, we've got a slope here and then a slope here. So it's negative and then becoming a less steep negative. So maybe this first slope is like -0.3, and this next slope is -0.1. Again, the exact numbers don't matter. It's just, is it increasing or decreasing? And we see that f prime of x is increasing because it is becoming a smaller negative number. It is -0.1 is larger than -0.3, and so that means that f double prime of x is greater than 0, and so that means that we're concave up at that point. Finally, our last interval from h to k. So over that last interval from h to k, from here to here, we see that we are increasing. The function itself is increasing. F prime of x is going to be greater than 0. The slope is going to be greater than 0. If we pick 2 different points over that interval, what's happening? So here's the slope at that point. Here's the approximate slope at that point. The first derivative, f prime of x, is increasing. The slope of the tangent line to the curve is increasing over that interval. F prime of x is also increasing. So we saw the original function f of x was increasing and its derivative was greater than 0. We also see that the derivative is increasing, and so f double prime of x is also greater than 0. So that means that over that interval, we're also concave up. We have, I think, each sort of type of thing going on. We have decreasing and concave down over the interval from A to B. Sorry, increasing and concave down. We have concave down and decreasing from C to D. We have concave up and decreasing from E to G. And we have increasing and concave up from B, or from H to K. So where is this function concave down? It's really concave down, maybe like starting about there, concave down, all the way to maybe about there. So over this whole interval, we're concave down. And then at some point, maybe around there, we switch to being concave up. So over this interval, we are concave up. And then over the next interval, maybe starting around here, we are concave down again. And again, one way to see that is that at any place where it's concave down, if we look at the slope of the tangent line, the slope of the tangent line is decreasing. The slope of the tangent line is getting smaller, or either less positive or more negative, versus when we're concave up, that means that the slope of the tangent line is increasing. So the slope of the tangent line is becoming a larger number. Another way to see this visually is that a function f of x is concave up over an interval if the tangent line to the function lies below the curve over the interval. So you can see the tangent lines that we drew to this curve over the interval are all below the function for concave up part, whereas for the concave down pieces, if we say, okay, what's the tangent line to this curve, the tangent line to this curve, the tangent lines lie above the function when the function is concave down. Another way I think about concavity is that the function holds water, if it, like an upside down umbrella, if it's concave up. So if there was like water sitting right here, like it would stay in there, it wouldn't leave. Versus if we dripped some water right here, it would roll down. So it's concave down if it does not hold water. It's like a regular umbrella. So concave down, a shape like this, and it's concave up if it's a shape like this. If it's a shape that would hold water, like an upside down umbrella. And any place where the function changes concavity and has a tangent line, in other words, when the first derivative exists and the concavity changes, that's an inflection point. So somewhere in here, maybe there, the function changes from being concave down to concave up. And so this point right here is an inflection point. And somewhere around here, maybe there, again, the graph changes from being concave up to concave down. And so that's also an inflection point. So anytime that the first derivative exists and the function changes from being concave down to concave up or vice versa, that is an inflection point. All right, so a function is concave up if its first derivative is increasing, that is, if the second derivative is greater than 0. It's concave down if the first derivative is decreasing, that is, if the second derivative is less than 0. If the second derivative is equal to 0, we say that it has no concavity. Let's look at some examples, where we might encounter concavity. So one example is you might hear in the news something like, the growth of the economy has slowed from 2% per quarter to 1% per quarter. Let's think about what's happening with the first and second derivative there. So if f of x is like GDP or some other measure of the economy, then the economy is growing. It was growing at 2% and now it's growing at 1%. So the first derivative, f prime of x, is positive because f of x, GDP, is increasing. So the economy is growing, f of x is increasing, and so the first derivative is positive. But in this situation, where the growth of the economy has slowed from 2% per quarter to 1% per quarter, the second derivative would be negative because while the first derivative is positive, the first derivative is decreasing. So the rate of change, which is positive, has decreased. So it was growing at 2% per quarter, and now it's growing at 1% per quarter. So it's concave down. So again, this function is increasing and concave down in this scenario of the growth of the economy has slowed from 2% per quarter to 1% per quarter. Here's a graph of retail sales over a period of time from the U.S. Census Bureau. Let's just look at a couple situations. So for example, let's see in this interval right here, we would be, so in this little interval, we're increasing and concave down. So as we move to the right in x, we're going up in y, but it's shaped like a regular umbrella. It's concave down versus, say, in this interval right here, we're increasing and concave up. concave up. And some other intervals say here we are decreasing and concave down. Probably the most common application of the first and second derivative are in the velocity and acceleration of an object. So f of x could be the distance of a car from a starting point, or it could be the position of an object. And in that case, the first derivative is the velocity of that object. The second derivative is the acceleration of that object. So let's think about this, this graph below of this distance versus time graph. And suppose that this is this car traveling along over a period of minutes, and this is the distance from the starting point. So here we are like at home or whatever. So what is the car doing at various intervals? When is this car accelerating? When are they braking? When are they stopped? When are they going at a constant speed? And also, where is f prime of t positive? Where is it negative? Where is it 0? And same thing for the second derivative, f double prime of t. Where is it positive, negative, or 0? All right, so let's think about what this car is doing over various intervals. Let's think about here, this first interval there. So we see here that we're starting at some point at home, the distance is 0, and then we start slowly, and then the distance starts increasing more quickly. So here, f prime of t is greater than 0. The first derivative is increasing. So if we the first derivative is greater than 0 because the slope is positive. And also, f double prime of t is also greater than 0, because if we think about some other point there and say, okay, what's happening to the slope at that point? The slope is larger as we go to the right. So f double prime of t is also increasing. This is concave up over that first interval. Now somewhere around, so somewhere in the next section, at some point here maybe, we have an inflection point because we go from being concave up to concave down. So here we're concave down. Because if we look at any 2 points and we look at the slope of the tangent line here versus the slope of the tangent line here, it is decreasing. So here we're concave down, but we are still increasing. So that means that f prime of t is greater than 0, the derivative is positive, but f double prime of t is less than 0. The derivative is decreasing, the slope of the tangent line is decreasing, and if we look at the tangent lines, they're above the curve, meaning that we're concave down. And so what would that mean? So that means that we're still, our distance is still increasing. Distance increasing. Our distance away from our starting point is increasing, so that means f prime of t is greater than 0, but we are decelerating. So we are decelerating. Maybe we put on the brake or just took our foot off the gas, but we're decelerating. We're not going as fast. We're not increasing in speed as we were before. Now, what about this next interval? So over this next interval, here we are just staying at a constant distance. So right here, the car is stopped. The car is stopped. F prime of t is equal to 0, so the derivative is equal to 0, and f double prime of t is also going to be equal to 0. So the car is not accelerating or decelerating, the car's distance is not increasing or decreasing, we're just stopped. And then the car sits there for a couple of minutes, so from minute 5 to 8, the car is just stopped wherever it stopped, maybe it stopped at a store or something. And then over the next interval, we are concave up. So we see that this is concave up. So concave up, shaped like an upside down umbrella. And if we look at 2 points along that interval, we see that the tangent line is increasing. So here, f prime of x, or f prime of t, is greater than 0, the function is increasing, and f double prime of t, the second derivative is also greater than 0 because the first derivative is increasing. And then over this last interval, it's a little hard to tell exactly what's going on, but I would say that we're going at a constant speed. It looks like this is linear. So it looks like this is linear. That means that f prime of t is greater than 0, but it's some constant k. And f double prime of t then is equal to 0. It's neither accelerating nor decelerating. We're just going at a constant speed. And so our only inflection point is right about here. So this is an inflection point right here where we change from being concave up to concave down. Here there is no concavity when the second derivative equals 0, and here also there's no concavity because the second derivative is 0 over the orange and red sections. Here, this is an inflection point because we change from being concave up to concave down, but there's no other place where, according to our interpretation, we change from a positive to a negative or negative to a positive second derivative. So that one point is our only point of inflection. One more application of inflection points that I think is kind of neat is in statistics. So normal distributions are like the most important distribution statistic. They're bell-shaped curves with different means and standard deviations. You might, if you've taken statistics, you might know that one standard deviation plus and minus, so the mean plus and minus one standard deviation holds 68% of the data. Two standard deviations away holds 95% of the data, etc. But the place where there is an inflection point, that's where we are one standard deviation above and below the mean. So here we're concave down, and here we're concave up. At those inflection points, those are those special places, the mean plus one standard deviation to the mean minus one standard deviation. And if you haven't had statistics and that doesn't make a lot of sense, no worries. I just wanted to connect it for those who do. So this video was just all about understanding what concavity is, how it relates to the second derivative. In the next videos, we'll do the second derivative test.